All right, hello. This is the second lecture for Chapter 1, Chemical Foundations. The first lecture really focused on measurements, specifically on the number part of measurements, and this lecture is going to focus on the unit side, manipulating units, metric system, all that jazz. It's going to be a blast. All right, so like I just said, meaningful numbers must have a measurement and a unit. So here's examples of measurements. So we have a dime is 1 millimeter thick, a quarter is 2.5 centimeters thick. Mass would be 5 grams, 120 pounds, 55 kilograms. You get the idea. So again, in this class, you really need to focus on always using a unit when you write a number. Numbers are meaningless without them. So the single most important part of this slide, though, is this box here. So we're going to get some practice and a lot of familiarity with the metric system over the course of this lecture and also throughout the class. And it's really important to know these base units because the metric system is all about changing scale by using prefixes that modify these base units. So if you haven't already, I highly recommend that you print off this periodic table that I have on Brightspace in the syllabus/overview section of our course. So the most important part of this is your periodic table. Second is the back has a lot of tables that we will be referring to throughout the semester. And the first table would be in the upper right-hand corner of that periodic table. The flip side is the metric conversion chart. It is identical to this chart right here. So it's just really nice to have that nice and handy. So like I just said, the most important thing to keep in mind is that all of these prefixes are modifying our base unit. So base units are going to be grams, meters, liter, and seconds. Right, just abbreviated as G, M, L, and S. So all this chart is doing is modifying that to put it to a different scale. So everything from here down is going to be representing very, very small values, right? We could also represent that with scientific notation. Here, we're representing very, very large values. So we're familiar with like giga. That would be modifying a byte, gigabyte, right? Megabyte. The International Standard System of Measurement is really, really convenient because you have this very intuitive way of talking about things on very different scales. So another example that you're probably familiar with would be like liter, right? So you have liter, which is abbreviated with an L, and then you also have milliliter, which we abbreviate with ml. So this M is a prefix which is modifying liters. We can find that here, milli. We see that it's representing a small value, and we have this power of 10 over here, which is our exponential notation that relates to the base unit. Okay, so we are going to use this chart in order to do metric conversions, and we're going to get a lot of practice with that. So let's just come over to another program that's a little bit more friendly for what we're doing. Okay, so let's say that we need to do a lot of metric conversions. And we're going to use this chart in order to help us get there. So specifically what we're going to be looking at is our exponential notation and then our prefixes, right? So our symbols that are identifying what scale we're working on. So let's start with something kind of familiar, and let's say we need to convert 35 milliliters to liters. So again, we're going to find milli right here. We follow that across, and it's 10 to the negative third, right? Yeah, let me get rid of some of this. Okay, so it's 10 to the negative third. So that is our relationship between milliliter and liter. Specifically, that means that 1 milliliter is equal to 10 to the negative third liter. You want to think of this entire column as, I like to say, it belongs with your base unit. Okay, so this is our relationship, and we're going to be talking about these kinds of relationships a lot in this lecture. And we have a way of kind of defining these relationships, and they are called equivalency statements. Right, so this is our equivalency statement, in that 1 milliliter is equal to 10 to the negative third liter. That is the same thing as saying that 1 milliliter would be equal to 0.001 liter. Okay, so the scientific notation is really, really helpful. Because it's going to allow us to do our math quite easily, especially when we get a little bit more complicated, and we'll get a couple examples like that. So we have 35 milliliters going to liters, and we have our equivalency statement. Now, all equivalency statements can be written as two conversion factors. So conversion factors are used to convert from one unit to another. So the conversion factor from milliliter to liters would be 1 milliliter over 10 to the negative third liter. Or you could also write it as 10 to the negative third liter over 1 milliliter. What's important to recognize is that 10 to the negative third liter and 1 milliliter are the exact same thing. They're just representing the same volume, the same value on different scales. So if we were to multiply by this value, that would be the exact same thing as if we were to multiply by 1. Right? They're the exact same value. We're not changing our quantity at all. So now we're going to go ahead and use that with our conversion from 35 milliliters to liters. So we would take our 35 milliliters and we're going to multiply it by one of these two conversion factors. Now the conversion factor, remember, they are equivalent, right? They mean the exact same thing, and it's exactly the same as multiplying by 1. We're just converting from one unit to another. So I'm going to select the conversion factor that will allow me to cancel out my milliliters and move into liters. So this concept is the same as if you were to take like the fraction 2 over 1 and multiply it by 3 over 2. Right? Those 2's are going to cancel out, and you're going to get an answer of 3 over 1, otherwise known as 3. Okay, so that same principle is being applied here, only we're multiplying by 1, and we're just converting from one unit to the next. So I want to choose this conversion factor because it puts milliliter in my denominator, right? All fractions are numerator over the denominator. Okay, so I want milliliter in the denominator, 10 to the negative third liter. And that's going to equal 0.035 liters, right? We're just moving that decimal place, right? My lowercase n in scientific notation is negative, which means I would be moving my decimal place to the left. Okay, so let's do a few more examples. All right. So let's keep it simple to start. So that one we were modifying that was liters, liters as our base unit. Now let's say we have 4,246 micrograms, and we need to go to grams. All right, so the first thing you want to do is recognize, right, that we have a modified base unit, right? Anytime you see two letters for your unit, you know that it's been modified. This time it's being modified for micro, which has this cool Greek symbol, and that represents 10 to the negative 6th. So what does that mean? How would we write our conversion factor? That would mean that 1 microgram is equal to 10 to the negative 6th grams. Remember, exponent always goes with the base unit. Another way of thinking of that is every time you have your modified unit, so you have your 2-letter unit, that is always going to have the number 1 in front of it in your conversion factor. Remember that conversion factor can be written two ways. We want to select the way that is going to cancel out our micrograms and allow us to navigate from microgram to gram. So remember, that is the only utility of a conversion factor, to convert from one unit to the next, because these are representing the exact same, in this case, mass. All right, so we have, let me change my color here. Perfect. We have 4,246 micrograms. Yep, we're gonna roll with it. And this is the conversion factor that I would need. That's 1 microgram is equal to 10 to the negative 6th grams. Now, how I just drew this is called a picket fence structure. So the picket fence is this part. You do not have to use a picket fence. I will always use a picket fence because it helps me stay organized and it makes it more intelligible for students. But this is exactly the same as what we did before. Right? This is the exact same setup. Here, it's just instead of using these parentheses, I'm just creating a picket fence. This is still my numerator over my denominator. Okay, so now I want to figure out what that value is, and this time I'm going to use a calculator just so we can talk a little bit about how to do exponential notation on your calculator. So all we're really doing is moving our decimal place. But for some problems, and especially moving forward in this class, you really want to be able to use, if you have a scientific calculator, you want to be able to use it to your advantage. So there are a couple buttons that you're going to want to identify on your calculator, and it depends on the kind that you have, what button it's going to be. One example, like mine, has a button that is EE. And what EE stands for is that's going to take the place of your times 10, right? So when I want to plug in, let's say, if I had the number 5 times 10 to the negative 3rd that I was plugging into my calculator, I would actually just plug in 5, and then I have to hit second because EE is written in a smaller font, different color, next to the button. So I would hit 5, second, EE, and then I just hit negative 3. This is input into my calculator. My calculator reads that like this. It's just really nice and streamlined. Another alternative, if you don't have EE, you might have a 10 to the X button. If you have EE, I would recommend using that. It is the easiest one. If you don't, or you can't find a button like that on your calculator, you can come to one of the recitation sessions and I'm sure I can help you identify it, or better yet, you can go on Google and you can just find the manual for your calculator and you'll be able to find scientific notation for sure. Okay, so let's get rid of this. If I plug that into my calculator, like I did, my calculator reports 0.004246 grams. Now I could also write that in scientific notation of 4.246 times 10 to the negative third gram. Cool. All right, let's do a couple more examples. All right, so for all of these, we've just been going from a prefix to a base unit. Now we're gonna go from a prefix or modified unit to another modified unit. So we've done liters, we've done grams. Let's do seconds, sure. So let's say I have 420, I guess I'm really into like 4, 2. Let's change that up a little bit. Let's say 974. 974. Let's do kilograms. I said we were going to do seconds. That's okay. Kilograms. And we're going to go to milligrams. Okay, so remember this exponential notation is all related to that base unit. So what you want to think about doing here, there's a couple different ways actually to solve this problem. There's always a couple different ways to solve the problem. I would recommend solving it the way that I am going to demonstrate, just until you get comfortable with the metric system, and then I'll show you a little shortcut. So we don't have a exponential notation or a mechanism in our chart of converting directly from kilograms to milligrams. So what we want to do instead is you want to think about building a little bypass where we're going to convert from kilograms to grams and grams to milligrams. And as we do this, you're going to see why that picket fence structure is a little bit more convenient than using parentheses. So first, let's identify what our relationship is between kilograms and grams. So kilograms is 10 to the third. Milligrams is 10 to the negative third. Oh, this will be fun. Okay, so we have 974 kilograms. And we know that that 1 kilogram, right, that's my modified, my prefix unit, is going to be equal to 10 to the third grams. And we know that 1 milligram is equal to 10 to the negative third grams. Okay, so I want to get rid of my kilograms and go to grams. So when I set up when I use my conversion factor, I'm going to put kilograms in the base, that's my dog, going to 10 to the third grams. Then, now I've successfully made it to grams. Now I want to convert from grams to milligrams. So this is going to be 10 to the negative third grams going to 1 milligram. Oop, sorry, didn't mean to delete that. All right, so you plug that into your calculator, and you'll get 9, that would be 6, 9.74 times 10 to the 8th milligrams would be your answer. which is pretty cool. Yeah, so you want to get familiar plugging that into your calculator. Another really good device is just to remember your rules for exponents. So in this case, if you're dividing exponents, you're going to subtract. So in this case, we had 10 to the third. You can think of that as being minus here, let me actually back up. Let's just look at the exponent. So you can think of that as just looking at our exponents, forgetting that it's a power of 10. You would just have 3 minus a negative 3 would be 6. So I would expect my power of 10 to be 10 to the 6th. Notice I just kept it in scientific notation, and I would have 1, 2 more decimal places to the left, so that would increase, right? Remember that nice device? That would increase that exponent, so that would be 10 to the 8th. If you multiply, you're going to add them. So it's just a really helpful device because you want to be able to look at the answer that you get and ask yourself, like, does this make any sense? And in this case, yes, it does. Okay, so this is just an example of using a bridge, of getting back to your base unit to work with your exponential notation chart. Okay, so those are all like simple units, but we can also have compound units. So let's look at a situation where we have like let's say we have 30, sorry, there we go. Say we have 35 meters per second. And we're gonna go to kilometers per hour. Sure. Okay. So when you see a unit like 35 meters per second, you need to be able to recognize that that is 35 meters in 1 second. Okay, so that's like a really, really critical understanding that that's what that represents. I think we get used to seeing things like mph, miles per hour, and you don't think about how that would actually translate to a rate, right? This is representing a rate. You travel 35 meters in 1 second. So now we're going to be converting meters needs to go to kilometers and seconds needs to go to hours. So I know I'm going to have a lot of conversions, so I'm just going to go ahead and extend my picket fence. So I have meters to kilometers, and I know that there are 10 to the third meters in 1 kilometer, right? I have 10 to the third kilometer. That power of 10 always goes with your base unit. So I have 10 to the third meters is going to be 1 kilometer. So at this point, I have successfully converted from meters to kilometers. Now I need to go from seconds to hours, right? So let's just do this piecemeal. I know that there are 60 seconds in 1 minute, and there are 60 minutes in 1 hour. Okay, you could also take 60 squared, 3,600, and just multiply by that. But we took it the long way around, which is fine. I don't expect you to memorize like conversion factors outside of being able to use this this chart, but I'll never tell you things for converting time because time is universal. No matter where you're from, you know that there's 60 seconds in a minute, 60 minutes in an hour, 24 hours in a day, 365 days, unless it's a leap year per year. Okay, so what's really nice when you have a more complex dimensional analysis problem, which is what we're doing right now, before we were converting within the metric system, now, well, we're doing essentially the same thing. But it's just a little bit more complicated because we have this compound unit, it's really nice to go through and make sure that the unit that you want, in this case kilometers per hour, is the unit that you end up with. So in order to do that, I want to look at my problem and I say, okay, I started out with 35 meters. My meters canceled out. I started with seconds. My seconds canceled out. My minutes canceled out. And I'm left with kilometer in my numerator and hour in my denominator. Get in the habit of double checking that your units cancel out correctly. Also make sure that you write your conversion factors correctly. So, two really big things to double check. It is amazing the number of times students would get a problem right if they had just paused to do this exercise. Okay, so let's plug it into our calculator. 35 times 60 times 60. Take that value and divide it by 10 to the third. You get 126 kilometers per hour. So one other point to make in how you plug this into your calculator is it's good practice to multiply across the entire denominator. Numerator. And then you want to divide by the product of your denominator. That's going to be really important, and we'll come across some examples where I can really illustrate why that is so important. But for now, we'll just leave it at that. Okay, so there's a ton of practice and recitation, lots of practice and worksheets. You want to make sure that you get this down. If you're having difficulty as you're working through problems at home, definitely schedule a tutoring session with me through Calendly or hop on a recitation session. All right. So what we were just doing is called dimensional analysis, and it's when you're converting from one system or scale of measurement to another. So the systems that we were just using were within the metric system, so they all make a lot of sense. It's just using those prefixes. But if we're also using the English Standard System, then we're going to have these equivalents. So for instance, 2.54 centimeters is equal to 1 inch. Again, I don't expect you to have these memorized. I will always give those conversions for you if it's needed in a quiz or an exam, but I will never give you conversions for the metric system because I've already given it to you. So just keep that in mind. Also, generally, if I give you a conversion factor, you're going to need to use it. So that's almost like me giving you a hint as to how to solve the problem. Okay, so again, these equivalents, just like we saw with the metric system, 1 meter being equal to 1.094 yards can be written two ways. The way that you use, or the conversion factor that you use, is going to be the one that allows you to make the transition that you want to make. So let's just do a quick example right here. Let's say that you had 46 yards and you needed to convert that to meters. So I'm starting with yards, and that would be in the numerator, right? So I'm going to want to select the conversion factor that has yards in the denominator, allowing them to cancel out. So I would have 46 yards, and there's 1.094 yards in 1 meter. So you take that 46, divide it by 1.094, and you get 42.05 meters. Now, using our significant figures, we're limited by our 46. Remember, conversion factors are not included in calculating significant figures because they are exact values, right? So I would need to round this to just 42 meters. Very cool. So what we just learned in metric system, we can apply to converting from the English standard system as well. So let's do another problem, and yeah, let's do another kind of more complex one, because why not? And let me get some conversion factors because I don't have that memorized. Let's say we have we have 46 ounces of tofu. Why not? Delicious. Okay, so we have 46 ounces of tofu, and I want to know how many pounds that is. Yeah, perfect. Okay, so we have 46 ounces, and I want to go to pounds. Okay, so a conversion factor that you would need to know is that 1 pound is equal to 16 ounces. Again, I would give this to you. So we have 46 ounces. We are starting simple. I need ounces to cancel out, so I want my ounces in the denominator. I want pounds in the numerator, so 16 ounces, 1 pound. 46 divided by 16 is equal to 2.875 pounds. Rounding that to two significant figures would be 2.9 pounds. Okay, so let's do a slightly harder problem. And then again, there's so many examples. I have a whole worksheet that's just doing dimensional analysis. I highly recommend that you practice it, especially if what we're doing right now is feeling a little bit overwhelming. Chemistry is more like a math class than any other science class you've probably taken. It's true of all the physical sciences, so including physics. You really have to practice problems. You have to get familiarity with the problem-solving strategies. So definitely plan on setting aside every week to get a lot of practice. Okay, so we're gonna do miles per hour going to meters per second. Kind of similar to a problem that we already did, but it's gonna illustrate why putting things into your calculator a particular way is really important. So let's say we're cruising on 95 and we're going 75 miles per hour. And I want to know how many meters per second that is. Okay, so remember miles per hour would be 75 miles in 1 hour. And it doesn't matter which one you start converting. If it's going to be hours or miles, doesn't matter. Let's start with hours. So I'm going to say that in 1 hour, there's 3,600. Nope, you know what? I'll do it the long way. So it'll help illustrate my point. So there's 60 minutes. And in 1 minute, there's 60 seconds. Okay, so my hours cancel out, my minutes cancel out. I end up with seconds in the denominator, which is exactly what I want. So now I just need to convert miles. So this would be an example where I would tell you this conversion factor, and that is that there's 5,280 feet is 1 mile. So that's one conversion factor that is really important. And then we also are going to need foot to meter. So one foot is 0.305 meters. Whew. Had to dig a little deep there. Let's go the other way. Okay. Again, these are values that I would give you. So let's go from miles to feet and then feet to meters. So 5,280 feet is 1 mile. And, oh, I did that wrong. Oh, good example, right? So if I were double check, my miles are not canceling out here. I made a mistake. Right, so it's easy as you're doing dimensional analysis problems to kind of get carried away, like I just did. You think about the next step that you need to make. So always just double check your work. So that's 1 mile, 5,280 feet. 1 foot is 0.305 meters. Okay, so this is where it's really important that you plug everything into your calculator correctly. So first you want to multiply across the whole numerator. So I take 75 times 5,280 times 0.305, and I get a value for that. And you should plug this into your calculator too to make sure that you're doing it correctly. Then I'm going to divide that, and in parentheses I'm going to take my 60 times 60. So that's telling my calculator to first multiply 60 times 60 and take that value and divide my numerator by it. So I get 33.55 meters per second. So just to illustrate why this is important, if I hadn't put those parentheses there, I would get, let's see, 75 times 5280 times 0.305. Take that divided by 60 times 60, I get a huge number, right? So 120,780 meters per second, which is really, really fast. Excuse me, I'm allergic to my dog, actually. Yep, smart moves. So make sure that you obey the order of operations. And such a faux pas right now. And get a lot of practice. Okay, so we're going to go ahead and move on. Again, you can come to recitation. We can schedule time to make sure that you get this process mastered. All right, so the last couple parts of this chapter are pretty straightforward. You need to be able to convert temperatures from one scale to another, one system to another. Really throughout this class. So there's going to be certain chapters where Kelvin is the temperature structure or system that we're using. Sometimes it's Celsius. We very rarely use Fahrenheit, but it is still something that you are expected to know. So we have Celsius and Kelvin. So let's look at these scales first. So this is Celsius and Kelvin. So Celsius and Kelvin are on the same scale. What's different about them is that they have a different 0 point. So Kelvin is an absolute system. So it is always positive. It goes down to absolute 0. Kelvin is a measurement of basically molecular motion, and so you can't get negative motion. Just keep it that simple. When we get to chapter 5, we'll talk more about the Kelvin system. So Kelvin and Celsius are on the same scale. They have different starting points. So that difference in scale, if you see here, we have 0 degrees Celsius is equal to negative 273.15 Kelvin. So if we're converting from Celsius to Kelvin, you would take your degrees Celsius plus 273.15. In this class, we just simplified that to 273. It would be equal to the degree Kelvin. So this is really common notation that you see here. Often we'll use a subscript in order to modify a variable. So this T is standing for temperature. TK is saying temperature Kelvin. This would be temperature in Celsius and temperature in Fahrenheit. Very common system used in the physical sciences. So you'll develop some familiarity with this as we move forward in the class. So this is our conversion from Celsius to Kelvin. Going the opposite way, we would just subtract that 273.15. So Kelvin and Celsius, same scale, 1 degree means the same thing. They're just starting at different points. Celsius and Fahrenheit are different. So the way that we think about this is basically, so degrees Celsius and degree Fahrenheit, they're different scales. And they're different zeros. So first, let's look at scale and how we're going to make those equivalent. So Celsius, at 0 degrees, water freezes. At 100 degrees, water boils. Very simple, very wonderful. For Fahrenheit, water freezes at 32 degrees Fahrenheit and boils at 225 degrees Fahrenheit. So that difference in degrees on the Fahrenheit scale from water freezing to boiling is 180 degrees, and on the Celsius scale it's 100. So if we were to create a ratio relating that difference to each other, it would be 180 degrees Fahrenheit and 100 degrees Celsius, which would simplify to 9 degrees Fahrenheit and 5 degrees Celsius. Okay, so this is the conversion or the relationship, the ratio of degrees Fahrenheit to Celsius that would allow us to put them on the same scale. Now we need to look at their 0 points. So 0 point for Celsius is 0, for Fahrenheit is 32. So putting that all together, if we're converting from Celsius to Fahrenheit, you would need to take your degrees Celsius, multiply it by 9/5, add that 32 degrees Fahrenheit, and you're going to get your answer in degrees Fahrenheit. And then here we see going the opposite direction. So those are really simple formulas. I'm not going to do an example in this lecture. You have practice and recitation. Come in the recitation packet, and also come to group tutoring sessions, whatever you want, tons of opportunity. So the last kind of mathematical relationship that we're going to be looking at is with density. So density is a great way of identifying a substance. It is an intrinsic value of the substance, so it's generally going to be the same, although density is affected by some factors like temperature and whatnot. But by and large, most of the time when you're looking at a substance, it's going to be at around 1 degrees atmosphere or sea level and room temperature. So density is equal to our mass over volume, and our lab for this unit is, or for this chapter, is all about density, so you'll get a lot of practice with this. The unit for density is usually going to be grams per milliliter. It could also be grams per centimeter cubed. So 1 milliliter is equal to 1 centimeter cubed. Right? Because actually volume is just a derivation of length. Length cubed would be your volume. Volume being milliliter, centimeters cubed. So this example here, this figure, is showing us a concept that's really drilled home in lab, so I won't go too far into it. We also have a word problem that's coming up that we'll work through that uses density by displacement. But a common way of finding the density of an irregular shaped object, such as this ingot of metal, is to have a specific volume of water. It looks like this is 150 milliliters or thereabout. You submerge or drop that ingot into, or that irregular shaped object, into that cylinder. The water level rises. That rising of the water level is due to the volume of that object displacing that water. So the volume of the object is going to be equal to that difference in height that we see here. Right? So that difference of height in the water level. Okay, so here's a great example, and we'll just work through it together. So let me actually give this a little bit more space. There we go. All right, so we have tungsten and gold have very similar densities. If a 45 gram metal ingot was dropped into a beaker containing 100 milliliters of water, to what height would it rise if it were tungsten, and what would it be if it were gold? Okay, so this is a really great opportunity to just kind of talk a little bit about our problem-solving strategies. And actually, I'm going to use my other program to work through this. Give me a couple seconds here. That way we don't have to worry about the words disappearing on us. Okay. So tungsten and gold have very similar densities, blah, blah, blah. So as we are working through this semester, we're going to be looking at more and more complicated word problems. Chemistry is all about word problems. So for a lot of students, word problems aren't that comfortable. It's not something that you like having to do. So there's a general strategy that we're going to be applying this entire semester. This is a easier word problem, but this same strategy applies to every single problem that we'll see. So word problem solving strategy. Okay, so the first thing you want to do is define your variables. All right, so let's just go ahead and do that. So we have tungsten, and if you look on your periodic table, you'll see that tungsten is one of those elements that doesn't have a letter associated. That makes sense. It's not just like T or TU, it's W. That has to do with its former names. So W is tungsten. We're given its density. So here's a good opportunity for us to use that system where we use subscripts to modify a variable. So we would have density tungsten is equal to 9.25. And remember, you always want to keep your units. So we have grams per centimeter cubed. Then we have our density of gold. It's another example where it's not GO. If you look, tungsten and gold are in the same row of your periodic table. Tungsten is element number 74, gold is 79, and it is AU. And that is 19.3 grams per centimeter cubed. What else do we have? We have a mass of 45 grams, and we have a volume. And this is the initial volume, so the volume before we add that ingot, and that's 100 milliliters. Okay, so we've defined our variables. That's everything that's from my word problem. What that essentially is doing is cutting out all of the stuff that I don't need to know, right? It's simplifying my problem and just cutting out the most important pieces so that you've essentially converted your word problem to just looking at your values. Some students find it really helpful to actually go through the word problem and underline those numbers in units. That's another way of kind of practicing pulling that information out. I still recommend making a chart of what your variables are. Okay, so then the next thing you're going to want to do is identify your formula. Okay, so in this case, we know that density equals mass over volume. This is the displacement problem. So in displacement, we're actually looking at our change in volume. So this triangle is the Greek symbol delta, and delta means change in. So change in volume. And anytime you're looking at a change in a system, you're always going to take the final place minus the initial. Okay, so let's go ahead. So that's our identifier variables. Then we are going to convert units if you need to. In this case, we don't need to convert any units. Everything's going to be in agreement with each other, but that's not always the case. And then the fourth is going to be set up and solve. So this strategy, again, is what you're going to be using this entire semester. So we will be adding some nuances. We'll kind of develop a more robust understanding of it. But yeah, you really want to get familiar with this. Okay, so we're going to be solving for volume, right? So the question is, what would the water level be if the metal were gold or if it were tungsten? So to what height or what volume will that water level get to? So what we're solving for is our volume. And this, I chose this example because solving for volume in the denominator is something that some students just really struggle with. So let's just go ahead and work through it. So we know in order to solve for volume, we're going to want to isolate it on one side of the equal sign. If it's in the denominator, we first need to get it out of the denominator. So the way that we're going to do that is multiplying both sides by volume. So my volumes cancel out on this side, and we get volume times density is equal to mass. Now I haven't accomplished my goal of isolating volume to one side of the equal sign, but I have accomplished the goal of getting it out of the denominator. So now I'm going to divide both sides by density, right? You have to do the same thing to both sides of the equation. Density cancels out, and I have volume equals mass over density. Now, anytime you solve a problem like this, you're basically just going to be swapping those two values. Totally ignore that when I just said that you hated it. Okay, so this is my working problem. And we're just going to solve for one because we don't need to do both examples. So we're just going to start with our density of tungsten. So volume of my ingot is going to be equal to 45 grams of tungsten divided by the density of tungsten, which is 19.25 grams per centimeter cubed. I plug that into my calculator, and we get 2.34 centimeters cubed. So this is the volume of that tungsten ingot, right? An ingot's just a chunk of metal. So if my water level started at 100 milliliters, it is now going to be at 102.34 milliliters. Right? Started at 100. This is the volume of my ingot. Now it's at 102.34. If it were gold, I just need to change this to 19.3 grams per centimeter cubed. You get 12.33, right? So this would be if it's tungsten. If it's gold, it's going to have a slightly lower volume because it's more dense. And you would get 2.33, so there would be very little difference if it was tungsten or gold. Okay, so again, you're going to have a lot of examples of problems like this in your lab. Okay, so the last part of this chapter is just some kind of basic concepts, so we're just going to roll through this pretty quickly. Remember the goal in this class in chemistry is to start thinking about matter on the atomic level. So we have these three phases of matter that we're all familiar with: solid, liquid, and gas. And at the molecular level, you have a lattice structure that forms in solids where those molecules are not really moving much at all, and they are in a rigid shape, and they occupy a fixed volume, right? So you have this lattice structure. Here we have solid ice, right? Notice that the solid ice has a lot of space in it. That is this molecular structure, the way that water molecules associate with each other in solid form, is what causes ice to float on water, which is pretty unique, right? Normally, if you have a solid, it would sink in a liquid of itself. Water is unique. Ice floats, which is awesome, because if it didn't, then our oceans would just freeze solid and there wouldn't be life on Earth. Okay, water is really important. So here we have our liquid. Liquids, those molecules are moving a little bit faster. They do have a fixed volume, but they're going to occupy the shape of their container. And then we have gases. Those molecules are moving much more quickly. They have a lot more kinetic energy. And they have neither a fixed volume or a fixed shape. So they are going to completely fill their container. Gases have some really interesting behavior. They're kind of sometimes hard to conceptualize. And because of that, we have an entire chapter, chapter 5, that is dedicated to gases. So matter is going to be able to kind of fall into two different categories. You have pure substances, which would be like if you had completely pure water, where it was just water molecules, nothing else, no ions, no sediments, that would be a pure substance. And then everything else is a mixture. So mixtures can be homogeneous or they can be heterogeneous. Homogeneous mixtures are things where if you look at it, it looks just like one material. So prime example there would be like coffee with milk in it. It just looks like lighter coffee. It looks homogeneous. You can't see the milk in the coffee unless you drink soy milk, and then you can. I'm sorry. Only because, yeah, the heterogeneousness is kind of gross. But if it's homogeneous, it all looks like one thing. So here's some examples: milk, salt water, coffee, mouthwash, alcohol. Cool. Heterogeneous mixtures are going to be ones where you can tell that there's multiple different kinds of matter in that mixture. So example, chocolate chip cookies, bubble tea, ice cream sundaes. Heterogeneous mixtures. Okay, so this last consideration for this chapter is the difference between a physical change and a chemical change. Physical changes do not involve a change in chemical composition. So there are a lot of different physical changes that can take place. You can have a solid melting to a liquid. You can have a liquid freezing to a solid. You can have a solid subliming to a gas directly. An example there would be like dry ice. Those are all physical changes. There's no change to the molecule itself. It still has the same form. It just has basically gained or lost energy. So chemical changes are when you have a reordering of chemical bonds and you have a difference in structure. So examples there would be if you burn wood, right? That process of burning is going to combust and use the molecules, break them down into simpler parts. In that breaking down, there's a release of heat. So chemical change, you have a new substance that's formed because the structure of the molecule changes. Your textbook does a really good job of kind of giving more examples of physical and chemical change. It also walks through ways that we can separate mixtures, which is just a really interesting introduction to things like chromatography, which are wildly important in chemistry. So read your textbook, and that's it for chapter 1. Awesome.